Welcome in our introductory video about process data validation and reconciliation in chemical and power industries. In this first part, we will show major sources of redundancy of data in chemical and power plants. Measured redundant data are due to measurement and other errors frequently in a conflict with valid laws of nature. This issue can be resolved by data reconciliation. We will also talk about the important problem of data classification as redundant or non-redundant and observable or non-observable. In general, we can meet in practice with several types of mathematical models. In the first important group are so-called first-law models. They comprise balances of mass, chemical elements, energy, and momentum. They are the main source of redundancy in process data. The second group comprises so-called thermodynamic models, which are also exact, but they contain usually unmeasured parameters, which lower the system redundancy. The third group contains empirical models, which can't be used for data reconciliation. A typical example here are so-called regression models based on statistical processing of historical data. There exist at least two causes of data redundancy. The first cause is the existence of two or more instruments measuring one variable. We can meet this type of redundancy nowadays with increased frequency in critical applications like our modern power stations, nuclear facilities, etc. The second type of redundancy is so-called spatial redundancy. It is caused by model relations among measured variables. The spatial redundancy will be the subject of this presentation. The most simple case of an industrial model is the mass balance. In this small example, there are two balancing nodes and 5 measured flow rates. For every node, we can calculate the balance difference, which is defined as sum of outputs minus sum of inputs. The balance difference equals 3 measured units for node 1 and similarly minus 1 measured unit for the node 2. We suppose that the system is perfectly tight and these balance differences are caused by measurement errors. In this example, there exists two flow rates, which could be calculated from two balance equations around the individual nodes. We say that such system has 2 degrees of redundancy. This flowsheet shows the component balance. The mixture of 5 light hydrocarbons I separated on the system of 2 distillation columns. In this case, we suppose that flows of all 5 components in all streams are conserved. In practice, due to measurement errors of flow rates and errors in analyses, this need not be true. In this simple chemical reactor, methane is burned in the contact with air. In this case, individual components are not conserved due to the chemical reaction. The conservation law holds for all chemical elements contained in individual chemical species. The heat balance around this simple heat exchanger is based on assumption that there is no loss of heat from the exchanger shell to the ambient. Let's suppose that all flow rates and temperatures in the heat exchangers are measured. If we calculate the heat flux from the hot stream and the heat absorbed by the cold stream, these values will probably be different, due to measurement errors of flow rates and temperatures. The last example shows the hydraulic system, for example the water distribution network. Aside of mass balance, the model comprises also the energy balance and modeling of flow in pipes. For an isothermal model, we need flow rates, pressures, and also geodetic heights. We can suppose that the model will not be exactly fulfilled due to measurement errors of flow rates and pressures. Moreover, in this case, there can be problems with the empirical character of modeling pipeline hydraulics. We can conclude this part of the presentation by finding that there is the need for consistent data which are in agreement with laws of nature. This can be achieved by data reconciliation. Next slides will be separated in the left and the right part. The left-hand side will show general concepts, the right-hand side will show examples. For data reconciliation, we need three kinds of information. The first is a mathematical model. We will suppose that such model is a set of generally nonlinear implicit algebraic equations. In such system of equations can be variables of three kinds: measured variables, unmeasured variables, and constants. This is illustrated on the right part of the slide. There are two equations among four flow rates. Flow rates 1, 2, and 4 are measured, flow rate 3 is unmeasured. There is no constant in this example. The second prerequisite for data reconciliation are measured values flow rates number 1, 2, and 4. The final prerequisite for data reconciliation is so-called model of errors. In this simple example, the model is represented by standard deviations of measurement errors for flow rates number 1, 2, and 4. Aside of three prerequisites for data reconciliation defined above, it is automatically supposed that some measured data are redundant, as will be shown in the next slide. Important for understanding data processing in redundant systems is deeper classification of measured and unmeasured variables. We talk about so-called redundancy and observability. This concept will be explained on this simple flow sheet. There are 3 nodes and 7 streams. Streams 1, 2, 3, and 4 are measured, streams 5, 6, and 7 are unmeasured. The balance around the node A contains 3 measured streams. The balance around this stream is overdetermined, measurement of one stream is redundant. Balance around node C contains one unmeasured stream 7, which can be calculated from the balance. Stream 7 is therefore observable. The balance of node B contains 2 unknowns, which are flow rates of streams 5 and 6. It is not possible to calculate unique values of these stream flow rates. Flow rates 5 and 6 are so-called unobservable. Stream 4 is nonredundant. This means that it can have any value without interference with other measured values. This slide summarizes previous findings and defines concepts of redundancy and observability. Measured variable is redundant if it can be calculated from other measured variables. Redundancy is one condition for data reconciliation. Unmeasured variable is observable if it can be uniquely calculated from measured variables. Here is the graphical presentation of the previous slide. There are 3 important consequences of the classification. The first, if the redundant measured variable is not measured, it becomes the unmeasured observable. The second consequence concerns measured nonredundant variables. If the nonredundant measured variable is not measured, it becomes unobservable. This holds also in the opposite direction. If the unmeasured unobservable variable is changed to the measured one, it is nonredundant. This slide shows the recon model of the steam cycle of a 660 MW power plant. It contains hundreds of variables and model equation. The classification based on the common sense is not sufficient for large models. Solving models of industrial size requires special algorithms and advanced software. To summarize, the classification of variables and solvability analysis is essential for solving large industrial tasks with hundreds or thousands of equations and variables. It is important not only for data reconciliation but also for design of instrumentation in new plants. Thank you for watching this video. I would like to invite you to the second part of this presentation, which will be about data reconciliation proper, benefits of data reconciliation, gross errors treatment, measurement planning and optimization, history of DRV. Here you will see also examples solved by Reckon. You can download your personal copy of this software, which contains also many solved demo examples of data reconciliation.